Okay. So in the last 3 classes, we were looking at the transmission of reflection of our electromagnetic waves, which is our typical TEM waves, our uniform plane waves. And we looked at the normal incidence, we looked at the oblique incidence, and in the oblique incidence, we looked at the perpendicular incidence, and then we looked at the parallel incidence. So these are the summary for the parallel incidence. So this is the reflection coefficient, this is the transmission coefficient, and this is the relationship between them. Then for the perpendicular incidence, this is the reflection coefficient. And then this is the relationship between the reflection and transmission coefficient. Then we have the Snell's law. So this is the Snell's law of refraction. And the Snell's law of reflection is the incident angle is equal to the reflected angle. So these were all, the things that we learned in the transmission and reflection of electromagnetic waves. There is just one last thing, one small part which is left in the transmission and reflection of electromagnetic waves, which is called as the Brewster angle. So first, before that, let me just remind you about the critical angle. So what is the critical angle? Yes, can Muhammad Al-Bosh, can you tell me what is the critical angle? You are there, Muhammad Al-Bosh?
Yes, yes.
So can you tell me, we learned about the critical angle, right? See here, we learned about the critical angle. So it is sine inverse n2 over n1. So what does this critical angle does? If my incident electromagnetic wave, if its angle of incidence to the boundary, if we make it equal or just greater than the critical angle, then what will happen? Talal, can you help him? Talal Jabar. Talal is not here. Okay. Abdullah Al-Shahri, can you help him?
Yes, Doctor.
Yes. So can you help him? What does the critical angle does?
I'm not sure.
Come on, guys, please start preparing for your final exam. Yes, Zuhair.
The critical angle is where the electromagnetic waves has not transmitted in the other region.
Yes. So this is what the critical angle is. So what will happen if you shoot your wave with an angle of incidence greater than or equal to the critical angle, then you will not have any transmission in the second medium. You will have complete reflection of the wave. That is called as the critical angle. So I hope Mr. Abdullah Al-Shahri and Muhammad Al-Bosh, so you will remember this, okay? So this is a special angle. That's why it is called as a critical angle. So in a similar way, you have another special angle, which is called as the Brewster angle. So what is this Brewster angle? It is nothing but there is a special angle at which you can get zero reflection. Instead of complete reflection, you can get zero reflection. See, zero reflection. And this is only possible in the parallel incidence case. So in perpendicular incidence case, you cannot. But for the parallel incidence case, it is possible to have zero reflection coefficient. That means total transmission. And at what angle? If you shoot that wave to the interface where you can get the total transmission or zero reflection is called as the Brewster angle. Okay. And therefore it is called as theta B, parallel. Why? Because this exists only for the parallel case, not for the perpendicular case. And how to find this angle? We know that when my angle of incidence becomes equal to the Brewster angle, my reflection coefficient must be 0. And if you take the reflection coefficient of the parallel case and equate it to 0, and then change the angle of incidence theta I to the Brewster angle, okay, and then solve this, okay. So you are simplifying all these things. When you simplify it, you will get this as your answer. And furthermore, if we consider that our medium is non-magnetic medium, that means I can say that mu R1 and mu R2, they are equal to 1. In that case, I can further simplify it and I can make this Brewster angle as tan theta B is equal to root of epsilon 2 over epsilon 1. This is called as the Brewster's angle. And this exists for parallel case. For perpendicular case, it does not exist. It's there in your textbook where you can go and you can look at the derivation. He did the derivation for both, for parallel and the perpendicular. But for the parallel case, it can exist. For the perpendicular, it's very, very difficult. Okay, so if you want to see it in the pictorial form, this is how it looks like. See? See? This is how it looks like. So if I take the air and glass interface, which is this one, so that means here my N1 is less than N2, where N1 is the refractive index of air and N2 is the refractive index of glass. And this is N1 greater than N2, where N1 is my refractive index of glass and N2 is the refractive index of air. So if you see here, so this is my red is my parallel incidence and blue is my perpendicular incidence. So what is happening? As the angle of incidence is increasing, slowly your reflection coefficient. See, this is my reflection coefficient. I'm not talking about the transmission coefficient because we can get it later. I'm talking about the reflection coefficient. So reflection coefficient, if you see here, the reflection coefficient, it increases slowly and then it becomes equal to 100%. This is for the perpendicular case. For the parallel case, it slowly decreases, but at a certain point, it becomes equal to 0 at a certain incidence angle. And after that, yes, it will increase and it will also become 100%. That means this is the region of my incident angle where I will get the TIR, total internal reflection, TIR, because here my N1 is greater than N2. So that's why here I can get the total internal reflection. So this is called as the Brewster angle. So how do you find the Brewster angle? Tan inverse, just now we got it, 1 over 1.5, which is equal to 33.69. And what is the critical angle? Sine inverse N2 over N1. So N2 is my air and this is my glass. 1 over 1.5, which is 41.8. So that's why at 41.8, you don't see any transmission. Now for the air-glass interface, here you will not see total internal reflection because the refractive index of air is smaller than the refractive index of glass, but you will see only the Brewster angle. And see the Brewster angle is somewhere here. And again, tan theta b is tan inverse 1.5 over 1, which is glass over air, because glass is 1.5, refractive index of glass is 1.5, refractive index of air is 1. So it is 1.5 over 1, which is 56.3 degrees. Okay. So these are the two special angles, the Brewster angle and the critical angle. Okay. So this actually concludes our part of chapter. Which chapter is it? It's the chapter of 11, which is our electromagnetic, chapter number 10, our electromagnetic wave propagation. So our chapter 10 was quite long. So now with this chapter, we actually concludes our electromagnetic waves. So in chapter 9, we looked at our Maxwell's equation, where we looked at how Maxwell modified one of the equation to account for the time-dependent fields. And then we looked at the lossy case, lossless case, and the solution of the electromagnetic wave and everything in our chapter number 10. Now, the next three chapters, chapter 11, chapter 12, and chapter 13, these three chapters, we will just look at the applications of the electromagnetic wave. Applications. Okay. So first, we will start with the transmission line. Then we will have the waveguide, and then we will have the antenna. And we will not go into too many detail or too many derivations, although for waveguides we have few derivations, but still we will focus more on, how you can use those equations. Okay. So shall we go to our next chapter? Any questions from your, say transmission and the reflection part? Okay, so let's start our chapter number 13, transmission lines. So now what are transmission lines? As you can see, the transmission lines, they are all now guiding medium. Okay, so till now in our chapter 10, we were looking at electromagnetic wave in an unbounded medium. Unbounded medium, that means there is no boundary. It is everywhere. The electromagnetic wave or our uniform plane wave is going everywhere. And it is available for every person. That's why it is everywhere. Now you can also have it, bounded. That means you will make sure that your electromagnetic wave travels within a bounding medium to a dedicated output, to a dedicated person. So this is nothing but your bounded medium. And your bounded mediums, it can be your coaxial transmission lines, it can be your twin wire transmission lines, it can be your planar transmission lines. I'm showing you some, pictorial forms. See, this is your coaxial cable, where the yellow here, wherever is the yellow is your metal part, and wherever is the green is your dielectric part. So this is your coaxial cable, right? And we have seen coaxial cables, the central conductor, the outer conductor, then the twin wire transmission line, two conductors covered with a dielectric. Then you have a parallel plate line where you have this top and bottom as your conductor, okay, which is nothing but your planar transmission line. Then these are, the upgraded versions of the planar transmission line, micro strip line, very common in microwave integrated circuit. Okay, so all these, and then here is your rectangular waveguide. How your rectangular waveguide looks like. See, so it is metallic waveguide with a cross section of a rectangle, and you can even have a cross section of a circle as well. And inside it is filled with dielectric. So all these becomes a bounding medium. That means all these will restrict your electromagnetic wave to travel just in a fixed say region. So that's why they are all bounding medium. And this is again our optical fiber. See, so here there is no metal, but you see the light blue, the dark blue is my center core, which is of different dielectric material, and the outside, which is the light green, is another dielectric, but its refractive index is smaller. And why we do not require any metals here? Because these two dielectrics will ensure we have a total internal reflection in this dark blue region, and therefore your light can travel. And this is basically meant for lights. That means the electromagnetic waves with the frequencies in hundreds of terahertz, like 150, 200 terahertz, which is our near infrared and our visible wavelengths. Okay, so now what we are going to do in today's class, if you see here, this is my coaxial cable. See, this is the coaxial cable, and now I am bringing both the summaries that we have learned in electrostatics and magnetostatics here. So if you see here, we have seen that for a coaxial cable, how the electric field is generated, how the electric field exists in the dielectric region. And these red arrows are my electric field. This is my electric field direction, right? This is in the rho direction. If this is my Z, which is coming out of the screen, then this is my rho direction. And in magnetostatics, we have seen how the magnetic fields are created. They are created in the A phi direction. See, the green ones, the A phi direction based on the direction of the current. Now, whatever we have studied in electrostatics and the magnetostatics, they also hold in the time varying case, where now my electric field will be changing the directions because of the alternate change in my source polarities. And the magnetic field will also change the directions. But they together, see, they are perpendicular to each other. See, so this is in rho direction, this is in phi direction, and they are traveling towards the Z direction. So the complete energy is carried by our electric field and magnetic field. So this is how the coaxial cable electromagnetic theory looks like. But in transmission lines, what we do, guys, we have two approaches. We have electromagnetic theory, we also have the circuit theory. But in most of the transmission line, we can deal with circuit theory, because circuit theory is relatively easier than electromagnetic theory. And therefore, in our chapter 11, we will go and we will try to use the circuit theory to understand a transmission line. But you will see that, in the circuit theory, the voltages and currents, they all satisfy a sort of, 1D traveling wave equation, and its solution will be very similar to what we got for our electromagnetic uniform plane wave solutions traveling in the unbounded medium. Okay, so this is our transmission line. The main objective is to carry the power from the source to the load. And this transmission line can be a coaxial cable. It can be twin wire. For the coaxial cable, the central part is the positive part, and the outer part is our negative part. Okay, so this is how our transmission line looks like. So the central conductor will be connected to this one. This is my central conductor, and my outer conductor will be connected to this. And here, the center conductor is connected to here, and the outer conductor is connected to here. So this is I'm just showing you how the connections are. So this is my central metallic conductor. This is my outer metallic. So this is how the transmission lines are connected. Now let's start. So now for transmission line analysis, okay, usually, in circuit theory, as you can see, we always dealt with lumped elements. Lumped elements or lumped element circuit, whatever you have studied in your EE202 or EE201, which is the new one, the electric circuit. Therefore, we considered the inductance, we considered the resistance as a lumped element. That means all the resistance exists in a certain small element. Okay, and we used this idea in our circuit. But now in our transmission lines, what will happen is we will go for distributed element circuit. That means my resistance, inductance, capacitance, they are not at a certain place, but they are distributed along the complete length of your transmission line. So that's why it is called as distributed elements. That means if you see here, the resistance, the inductance, the capacitance, they are now all distributed along the length. So that's why we usually use the terms resistance or capacitance or inductance per unit length. Okay, and why we do that? This is the thing, especially, it depends on your operating, say signals frequency. So your lumped element will work very well. The lumped element circuit theory, it works very well when the circuit interconnecting lengths, they are small compared with the wavelength of the signal. That means the L is less than or equal to 0.1 lambda. Then you can use the lumped element circuit. So the interconnecting lengths within the circuits, okay, if you can think of a PCB, so the interconnecting wires between the PCB and other things, those should be less than or equal to 0.1 lambda. Then you can use the lumped element circuit analysis. But if this doesn't, satisfy, where your interconnecting lengths are becoming way greater than 0.1 lambda, then the lumped circuit analysis or the lumped circuit theory, we cannot use that. And then we have to use for the distributed element circuit theory. And this is very common for our power transmission lines because we are carrying the power for hundreds of kilometers. So therefore, these are not satisfied. And now we will go and we will look at the transmission line from the distributed element theory, from the distributed element circuit theory. So how do we do that? And then we will also get what is called as telegrapher's equations. I will show it to you. So how we will start that? I have a very long transmission line, but what I will do is first I will just take a part of the transmission line. Okay, see here, this is what we do. I'm taking this much small length of my transmission line, and I'm saying that its length is delta Z. And this is the direction where my voltage and my currents are moving, traveling. But now if you see here, my voltages and currents, they are now not constants. They are now a function of the distance and time, because the length of my interconnections is very long. It doesn't satisfy this condition. So that's why we have to consider the current as a function of the distance and time, and voltage also as a function of distance and time. And here I'm considering the distance Z because this is my propagation direction, which is Z direction. And that's why you will now end up with 1D equations because of one space and time. Now, so what is our main objective, guys, here? Our main objective is, if at this end, if this is my current and voltage, then at this end, what will be my current and voltage? Once my current and voltage travels a distance of delta Z. This is what we are trying to see. And if we can get it for this small length, then we can easily generalize it for any length of interconnection. Okay, so now how to do? So here we start. So first, we assume these are the characteristics of our transmission lines: resistance per unit length, inductance per unit length. So here, I'm not saying R over L. I'm just directly saying that my R is the resistance per unit length, L is the inductance per unit length, G is the conductance per unit length, and C is the capacitance per unit length. Now here, I just wanted to emphasize one thing. Now there are different models that we can use to model this transmission line, the small transmission line of length delta Z. There are several models. Here, what we are doing, we are using this model. This is called as L model. There are other models like T model and pi model, but we are using L model. So in L model, if you see here, you have a resistance R. Now I'm multiplying it by delta Z in order to show it as a lumped element, because R is my resistance per unit length. Now, if this is my length of my transmission line delta Z, and if this is my starting point Z, and this is my end point Z plus delta Z, then the resistance of this transmission line, I'm putting it as a lumped element here, R times delta Z. And the inductance of the transmission line, I'm putting this as L times delta Z. Then I have a capacitance in parallel, C times delta Z, and I have a conductance, which is G times delta Z. Now, what does this resistance and inductance, they are actually representing? This we have studied in our previous lectures. See, the resistance, conductance. Resistance, this is what? This resistance is in series. That means this is the resistance which is basically coming from your conductor. Okay, your conductors. Your center conductor or your outer conductor. It is basically coming from the characteristics of that conducting material, which is coming from the conductivity. So this is that resistance. Then what is this? This is called as conductance. Now this conductance is basically coming from the dielectric material. It is coming from dielectric material, resistivity or conductivity. So you should not get confused. And this is from your metal, your conductor. This is from conducting metals resistivity. So this is that resistance. And that's why this is in parallel, because the dielectric material is between the two conductors, right? It is between the two conductors. So that's why you have a dielectric material, so your conductance in parallel, and the resistance is always created between the two conductors, two metals, which we have already seen in our previous electromagnetic core and our electrostatic part. That's why you have a conductance here. We have also seen that they will give the inductance. This inductance is also. Okay, so this is how you put the different elements in this manner. So putting these elements in this manner is called as L model. You can put the elements in other fashion as well. Then comes T models and pi models, but which is out of the scope of our class. So this is what we have now replaced our small transmission line of length delta Z with a model. Okay, so now our objective is, if you see here, so now I'm assuming that at this end, this is my voltage Z comma T. This is my current passing I of Z comma T. And this is at the end of the transmission line. This is the voltage, which is Z plus delta Z comma T, because it has traveled a distance of delta Z. And this is my current. And as I told you, our objective is to find this currents and this voltage. So now I'm assuming that this is my IX current, which is flowing here. And this is I1 and this is I2. So now, rather than going to the electromagnetic theory, we can try to solve it with a much simpler, the distributed element circuit theory. So what we are doing here, now again, we are starting with the Kirchhoff's voltage. So we are applying Kirchhoff's voltage. So what we are getting, minus V plus R times I plus L times I plus V. So what I'm doing, I'm just applying Kirchhoff's voltage law here. This to the outer loop, inductor, and this voltage here. So that's why I'm getting this voltage here, here, and this outer. So using this, I get the first equation. And now I'm rearranging it. So I'm bringing these two voltages together. And then I'm dividing it by delta Z. So I will get this plus Ri, this plus L times dou I over dou T is equal to Z. This is the equation. Now, this is for the length delta Z. But in reality, we are doing this mathematically for a small length of delta Z, small transmission length of delta Z. Okay. But this small delta Z, it should tend to 0, right? Because it's an incremental distance, incremental length of the transmission line. And this incremental length of the transmission line, if I make it as small as possible, then I can replace this with, what is this one? If you remember mathematics, then what will become this one? It will be, if I say limit delta Z tends to 0. Yes, this is the definition of what?
Derivative.
This is the derivation of the derivative. So then I can replace this with a derivative, which is dou V of Z comma T over dou Z plus this is as it is plus this is as it is equal to 0. Or if I take this on the right hand side, then the left hand side is equal to minus of this one. Okay, so this is when applying the Kirchhoff's voltage law. Now we are applying Kirchhoff's current law, KCL. So where I am applying here? Here. So Ix is I1 plus I2. And now what I'm doing? I'm writing I1 and I2. So what is my I1 and what is my I2? So first, my I1 is the capacitance current, which is C delta Z dou V Z plus delta Z of T over dou T. Why? Because voltage across this capacitor is same as this output voltage, which is V of Z comma delta Z comma T. Now, so Z plus delta Z comma T. So that's why I'm getting I as C dV over dt. So that's why it is C dV over dt. Then here conductance. It is conductance. So what is the current I? I will be not V over R. I will be V multiplied by G, right? I will be V multiplied by G. So again, the same. So what is the V here? The output side, because it's parallel. So the voltage which we are seeing at the output will be the same voltage that will be appearing across the capacitor as well as across the conductance. So that's why it is G delta Z, V of Z plus delta Z comma T. Now after this, again, Now, so what is my I of X now? I'm now trying to find what is my I of X. So this is the right hand side. I got the right hand side. Now I'm rewriting the left hand side, I of X. So what is I of X? If you go here, my I of X is nothing but this current minus this current, right? So this current is I of Z comma T minus this current, which is I of Z plus delta Z comma T. So this is my left hand side is equal to, this is my right. Now again, if I simplify, if I first divide it by delta Z, then I will get this one. There's this right hand side. And again, if I do the same thing, because my transmission line is of incremental length, so if I make delta Z goes to 0, then again, this term will become limit delta Z goes to 0. And this is the definition of the derivative. So that's why it is dou I of Z comma T over dou Z is equal to this one. See, so there is a negative. So I have to take negative common. Then it will be the definition. So that's why I am getting I, because the definition is I of Z plus delta Z comma T minus I of Z comma T over delta Z, limit delta Z tends to 0. So that's why I will take minus common. This is the expression. And if I bring this minus on this side, this is the expression. So now with KVL and KCL, we got two equations. So therefore, what are those two equations? These are the two equations. First for the voltage, another is for the current. And again, if you see them, they are coupled. Very similar to our magnetic field and the electric field. They are coupled. See, voltage, current, current, voltage. They are coupled. And these equations are called as telegrapher's equation, the 1D traveling wave equations, telegrapher's equations in the time domain. Now, what we need to do now? We need to now go and solve these equations to find my voltage and my current. So now how to solve it? We will first remove the time dependency. And how did we remove the time dependency in our EM when we were talking about the electromagnetic wave analysis? We took the help of solving it in the frequency domain. That means we remove the time domain, assuming a dependency of e power j omega t, and therefore we worked with phasors. And with phasors, it becomes much easier, where we can change any time back to the instantaneous or the time domain form. So here also we will do the same. So we will change this to phasors. So if I change this to phasors, then what will happen? Then I'm now representing V of Z comma T phasor as Vs of Z, and I of Z comma T in phasor as Is of Z. And therefore this is the time derivative. So the time derivative will be converted to just multiplication by j omega. So it is j omega L Is of Z. And similarly, we will do it. So now these are the two equations which we need to solve. Now furthermore, what we are doing, we are taking Is of Z comma here, common here, and Vs of Z common here. So if I take the common, I'm getting R plus j omega L, and here G plus j omega C. Now, yes, so you have already studied the circuit theory, both, 202 and 213. So what is this R plus j omega L, guys? Yes, what it is called?
Impedance.
Omega L. It's called the
Impedance.
impedance. So that's why I'm saying it as impedance, which is R plus j omega L. And what is G plus j omega C? Is called as admittance. So I am replacing it with its notation Y, which is G plus j omega C. So now my equations have even simplified further. So these are my two equations that I need to solve. And they are coupled again, still they are coupled. So now what we are doing in order to solve, I need to now substitute one inside the other. So I will substitute 3 into 4, very similar to how we did in our Maxwell's equation. In order to get the wave equation, I substitute the Maxwell's equation, in the Ampere's law, I took the Ampere's law and substituted in the Gauss law. So here also we are doing the same. So I'm substituting 3 in 4. So instead of Vs of z, I'm substituting this part. And then we will simplify further. And then what we will see is, we will see a second order differential equation, ordinary second order differential equation, which is this. So here on the right hand side, I am seeing this r plus j omega L times g plus j omega c. And this I am assuming that this is my gamma square. And therefore, I'm getting this expression. D square Vs of z over dz square is gamma square Vs of z. Or let us now drop z. So that's why I'm saying at d square Vs over dz square is gamma square Vs. And in a similar way, if you substitute equation 4 in equation 3, you will get for the current. Or if I drop z, it is d square is over dz square is gamma square is, where my gamma is root of r plus j omega L times g plus j omega c, or root of z of x. Okay, so these are nothing but, these are now these equations are now your telegrapher's equations, but now in the phasor. Now we need to just solve it. So how do you solve it? It is a very, straightforward, because this is an ordinary second order differential equation, and its solution is nothing but the exponential. So it has two solutions, very similar to our EM wave. When we were talking about the lossy case, in the lossy case, see, my Vs of z will be a V naught plus a constant time e power either minus gamma z. Okay, and then V naught minus again a constant time e power plus gamma z, So both are the solutions of this differential equation, both this one and this, both are the solutions. Now what is this gamma? We use this gamma, it's not a coincidence. Specifically, we named this as gamma because this gamma is in now, if you look it from the circuit theory point of view, this gamma is nothing but your alpha plus j beta, which will be root of this. So the real part of this will be alpha and the imaginary part of this will be beta. And not, so therefore your gamma here is the propagation constant. Alpha is the attenuation constant, beta is the phase constant. This is in the circuit theory. Very similar to what we have seen in the electromagnetic theory. And if I now rewrite gamma in terms of alpha beta, these are my solutions. E power minus alpha z, e power minus j beta z, e power plus alpha z, e power plus j beta z. So these are my solutions. And now if we go and if we get back our instantaneous form, you can get this into instantaneous form anytime. How we do it? Multiply by e power j omega t. See? Multiply by e power j omega t and take the real part. Take the real part. So what I am seeing? I am seeing as V0 plus e power minus alpha z cos of omega t minus beta z. This is the solution of my voltage V of Z of t in the time domain. And when you look at this answer, it is again clear that it is also a traveling sine wave. See, it's a traveling sine wave. And it is, sinusoidal. It is traveling wave, sinusoidal. And what is its direction? Its direction is plus Z direction. And attenuated by this term. And what is its field amplitude or voltage amplitude? This. So voltage amplitude, attenuation, this is what? Angular frequency, phase constant, and positive Z direction. And it is traveling with what velocity? Phase velocity with U, which is omega over beta. Okay. So this is for the positive traveling solution. Now, if you take the second independent solution, which is e power j beta z, which is this one, V naught minus e power alpha z e power j beta z. Again, if you want its instantaneous form, multiply by e power j omega t, take the real part. And again here, what we are seeing that this is also a traveling solution because this is a cos omega t plus beta z. It's a traveling sinusoidal wave. Plus, that means this is the solution which is representing that the wave is moving in the minus z direction and attenuating again as alpha. And this is the amplitude of my voltage wave. This is the frequency. This is the phase constant and the same phase velocity, which is u is equal to omega over beta. So V0 plus is nothing but the voltage amplitude of my wave going in the plus z direction. V0 minus wave is the voltage amplitude of the wave propagating in the minus z direction. Okay, so this is for the voltage waves where I substituted, where we were looking at equation 5. Now, in a similar way, you can look at equation 6 because in terms of mathematics, the differential equations are similar. So therefore, your current solutions will also be exponential. See here, exponential, the minus gamma z plus gamma z, instantaneous forms, positive traveling, that means plus z traveling, minus z traveling. This is the attenuations, both attenuating along the direction of the propagation. Yes, Zuhair.
Yes, Doctor, for quickly, but what is V0 plus and V0 minus?
This is this is the voltage amplitudes. That means our starting voltages you can think. And then as you move along the direction of propagation, this value will decrease. So this is, you know, if you want to relate it to the EM, this is our electric field amplitude. Got it?
Yes.
So it's just our starting values. So our initial values of our voltage and of our current. So here, the voltage amplitude, for in the positive direction, negative direction. So for the current also, you are getting the same. And again, now, here in a similar way, you can also define the characteristic impedance of the transmission line, which is Z0 is nothing but V0 plus over I0 plus. This is for the forward propagating wave or plus Z propagating wave. Okay, Now, what we are doing is here, okay, so we have, so the time is finished. Just give me a minute. So what we are doing here, we are just using this, our equation 7 and 9 in 3. So which is our solutions. So where is my 7 and 9? Sorry, here. My solutions, this is my 9. And this is my solution for the voltage wave 7. And if I put back in this equation 3, I can get what is called as the intrinsic impedance or the characteristic impedance of the transmission line. So if I put them back, the solutions, and if I simplify, this is the value of the characteristic impedance or the intrinsic impedance that I will get, which is root of R plus j omega L over G plus j omega C, which is root of Z over 1. This is called as the characteristic impedance, which is V0 plus over I0 plus, or it can also be equal to, you will see that minus V0 minus over I0 minus. Okay, so this is the characteristic impedance of our. So I think we will stop here and we will continue tomorrow. Okay, guys, so we will meet